Let me introduce though we have discussed RDDs and all the other things in the earlier session, but still I feel that some connect is there actually. Again, to understand RDD fault tolerance kind of the mechanism, which is I felt that quite interesting and definitely helpful in your programming journey also. Okay, so that's why I'm bringing up this particular thing. And let me give you the context of this RDD and how we can make use of the persistence and as well as the caching and how basically Spark is giving the fault tolerant mechanism on top of this RDD. Okay, so we pretty know that if I'm specifying this RDD orientation, we know that the term resilient distributed
Data set.
data set. Yeah, okay, resilient distributed data set. And moreover, we will study and all these data and distribution. That's fine. But apart from that, now I want to pull some of the points. How Spark sees the RDDs. So the Spark data, okay, whatever the objects, Spark data objects, okay, are called as RDDs. We are slowly observing in the context of this particular RDD, we generally observe that if any problem is there for the corresponding data or partition, then Spark is able to recollect that. But we have not digged that in what way it is getting back those kind of the partitions and how it is maintaining the data loss. So that is definitely I'm going to update on that before closing of the session, and hope you will be getting the clarity after the completion of this session. Definitely, okay.
Okay.
Right, and moreover, this particular RDDs again, if I'm talking, okay, these RDDs are subdivided into. Okay, these things are subdivided into actually partitions. Okay, because we studied about the partitions in terms of narrow and as well as the wide transformations. Okay, so this just there is a connect like spark data objects were initially we are naming as RDDs. RDDs are again subdivided into the partitions. And now the point is, okay, so these partitions, whatever I'm talking about, okay, so these kind of the partitions are distributed. Okay, why that name RDD came into existence, we can get the clarity with understanding of these things. These partitions are distributed across multiple random access memories. Because we always say that our RDDs are in-memory computing things. Okay, so these multiple RAMs of multiple okay slave modes, whatever the slave nodes I'm having, and are processed in parallel. Okay, see here, many answers we are getting actually. Um, So basically, we started with the RDD, and RDD again subdivided into the partition. The partitions are distributed across multiple machines because, as we are always saying, in-memory computing. Okay, we are saying that in-memory computing. Then obviously, this particular in-memory computing is preferring the random access memory. We pretty know that the primary memory, whatever we are studied in our engineering days or in the earlier days of this computer science. So just you can make use of that in memory as the random access memory kind of thing. And most important point, guys, here. Okay, so RDD programming style, because for every kind of the construct, maybe if I'm talking about the Python, there is a list and there is a set and dictionary. Each and every data structure is having its own kind of the storage and access mechanism. Similarly, the RDD programming style is data flow. Okay, it flows in terms of data orientation. So the programming follows the aspects of the data flow. So let me define what exactly the data flow is. Now, if I am talking about this data flow, which is nothing but a sequence, okay, some sequence of or sequential collection of information, or else is a sequence or collection of pipes. Actually, if you observe, friends, pipelining is a most important aspect in the machine learning, ML pipelines, all those kind of things. But before starting the machine learning kind of the algorithms, the Spark RDD itself is having the concept of the pipes. Okay, so it doesn't mean that until ML we need to wait for the pipelining or pipeline kind of the programming. But basically, with the RDD support, okay, in the context of this data flow, we can make use of the sequence or collection of the pipe. Now we need to define a pipe. Okay, what exactly this pipe is? Is a data operation. Okay, whatever the operation, I will introduce which are all the operations available, such as, and of course we pretty know them. Okay, such as loading the data. Maybe I can see some sort of the source data. I want to load that particular data and transforming the data. Okay, so just I want to transforming the data. Maybe I want to apply some kind of the transformations. Like, while working with the ETL kind of the process, maybe the data is not in the proper format or maybe the required format which we are looking for. In that particular case, we can apply certain kind of the transformations. Okay. And then we pretty know that this filtering where based on the some sort of the conditions I want to filter some kind of the data and then grouping the data. Okay, grouping is something like our SQL group by option, similar to that, and then merging the data, maybe joining all these kind of the data, merging data, etc. Now you see, guys, here. Let me show you the hierarchy. The RDD, okay, just we have taken as a subdivided into partitions, and again these partitions. If you observe these kind of the partitions, these partitions are distributed among multiple machines, like partition 1, 2, 3. I'm having the slave machine 1, slave machine 2, slave machine 3, and on top of this memory orientation, they are trying to execute. They are trying to execute. And apart from these kind of the convention, these aspects are following the mechanism of the data flow. Follow the mechanism of the data flow. And this data flow contains pipes, and this pipe is nothing but suppose if I'm taking some operation, loading is one kind of the operation on a particular partition, and then after loading, just I want to apply some filter. This is another thing, another slave machine, and after that I want to apply some group by, okay, on top of some other partition. Okay, maybe multiple machines were there which are parallelly running all these kind of the things. So the entire aspect, okay, starting from the partitions until this particular operation, it is leading to the parallel processing, and it is combining all these different kinds of the operations. Now, if you are referencing one interesting fact, guys, here, the most important thing is in Spark. Okay, as we are studying the architectural aspect along with the optimizations and fault tolerance kind of thing, the general approach here is the data flow is executed, whatever the data flow we are talking about, which is a combination of the pipes. Again, how do you define the pipe is a set of operations. Maybe that is a loading, filter, group pipe, okay, certain combination of the operation. This data flow is executed in sequence. Okay, because let me give you the reason. The output of this operation is input of this thing. Okay, and then the output of this operation is input of the next. So if these things are running parallelly, then how do you will achieve the accumulation or proper results, friends? Because after running this particular operation, then only I'm going to get the outcome. That outcome is connected with the next thing, and then it is going to generate the output, and which is connected as input to the other one, and finally we are going to get the result. Okay, so in Spark, data flow is executed in the sequence. That is, and in which manner? RDD by RDD. Okay, one after another. Whatever the operation we are following, one after another. Now, and one more point I want to add here, so that to summarize with in-memory computing. Okay, with in-memory computing feature and persistence feature. Okay, so today the persistence I'm projecting you in a different way, guys. Okay, just observe here in Spark, data flow, of course, which is executed is a combination of pipes with certain operations like loading, filtering, group by, all these things, and in the sequential manner. The reason already we have seen, because one partition or one activity's output is input to the other activity. So definitely these things should run in the sequential manner. And the entire operation is revolving around the RDD one by one or one after another within the in-memory computing. Okay, within the in-memory computing feature and persistent feature. And if you are referencing all these kind of the conventions, let me give you a basis. Okay, how these kind of the RTDs are working and all these kind of things. But before that, let me clarify. I'm saying that some sort of the operations actually. So in that particular case, there is some kind of on RTD. Basically, friends, two types of operations we can see. Operations can be performed. Okay, yes, you are right. The first thing is the transformations. However, we know pretty that the first thing is the transformation. This is the operation where one can observe that the lazy evaluation and all those things. And then you can observe the actions. And then you can observe the actions. Now, uh, we are exploring in a different way, guys, because this aspect is RDD, how it is helping us in the fault tolerant mechanism and what exactly the persistence in the manipulation and understanding of the data. So there are a certain kind of the transformations, friends. Actually, I can say there are three types of transformations basically. Because as of now, you can observe transformation, we know that is a lazy evaluation. And until the action is performed, there is no running of the transformation. But now you see, again, the transformations, there is a chance of applying some operation on each element. Okay, such kind of transformation is known as each element transformation. That means how many elements are there in a particular list or in a particular source. On top of each element, if I am applying some kind of the logic, then that is a each element transformations. Exactly. The examples are map and flat map. These are all the examples of the each element transformations. Suppose maybe if I want to apply X is the value and I want to add maybe experience of the employee in every year, we have to increment one. Okay. So in this particular case, just this experience of the employee after a year automatically should be incremented. So this is reflecting to all the elements in the corresponding storage. Such kind of things can be observed into the each element transformation. Second thing is the most commonly used kind of thing, the filter transformations. Okay, so in this particular filter, transformations such as directly I can use the filter. Okay, or else if I want to apply, there are certain aspects like filter by range. All these are the examples. Now, in sort of the filter, maybe I can apply the filter like that filter. So x if I'm taking the experience value, if x greater than 5, so something like that. Only on top of these particular things, maybe some 12% hike if I want to plan, then for those guys. So this particular filter is not going to apply on every element, friends, unlike in the earlier each element kind of thing. Map and flat map are applicable to each and every element, but your filter transformation is not going to reflect. on all the kind of the data items. There, what they do is just it is making use of some filtering, and only on top of that it is going to apply. Next thing, friends, as we expected, aggregated. Okay, so these are all aggregated transformations. Okay, the third kind of thing, which is typically the group by key. Okay, and count by key. All these kind of the things. Group by key, sorry, group by key kind of thing. So now we will pretty clear that a transformation actually up to now just we observed the some lazy evaluation. All these kind of activities are triggered whenever the action is done. But in the most common way, if I need to categorize the way how the transformation is leading, is each element transformation, filter transformation, and as well as the aggregated transformation. Like that, and if I'm talking about the second kind of the operation, it is pretty, of course, which are our favorite kind of thing. And simply, though we are knowing again, just I am reflecting that when an action, okay, so when an action is performed, okay, whatever the action we have performed on RDD. So suppose on top of the RDD, because we are conceptualizing that RDD basically, then only the data flow will be executed. And here, after reflecting this action, whatever the data flow we are talking so far, then only the data flow will be executed. Okay, so for what we have seen is just the action triggers the corresponding Spark execution. And if I am asking you guys, like collect is one of the action, and similar to that count. Okay, all these are some of the examples where one can refer related to the transformations. And sometimes, I can store my data into Hadoop distributed file system, like save as text file. Okay, so all these are some of the usages of the actions. Now, I'm putting you one more kind of thing guys here. So suppose I'm having certain kind of the transformations. I'm giving a data flow for you guys, R3. And from this R3, just I'm having three flows of the data, maybe R4, R5. And here I'm having R6, R7, R8, R9, something like that. I'm having the activity. Now you see, up to this particular thing, the execution results like R1 output will be given to the R2. R2 takes the input from output of the R1, and it is going to generate some kind of the data. It generates the output, and this output acts as the input for the R3. Now, the most important point here we need to observe is, guys, just I am observing this way: R1, R2, R3. Okay. Now, R1, okay, by submitting the output to the R2, it will be deallocated. Observe this, most important thing. Because all these RDDs, if you remember, guys, they are running on RAM. Keeping only one RDD, only one RDD is a mechanism followed by Spark, followed by Spark. Similarly, after R2, just it is giving the output to R3, and your R2 will be deleted. So at a time, I can able to get the latest R3 in the memory. Now the point here is so R3 output will be given to the R4. R4 output will be given to R5. And R5 again, R5 dot action, if I am taking, so that is my result actually, whatever the result. Now, while sending this output to R5, R4 will be removed, but R3 cannot be because it is there is a dependency actually. So again, R6 where we are taking the output, and then R7. So just we can make use of the output R7 dot action, which is the result. Similarly, R8 is giving the output, and then it will be removed, and R9 dot action, which is the result. So at the moment, this R3 is given the output to all these R4, R6, and R8, then only R3 will be deleted. Okay, so just the common output, of course. There is no multiple outputs, friends, because this is a connector where there are multiple flows pointing to this particular R3. So now the observation is keep these points in mind, and I'm coming up with some kind of the scenarios. Now the options are like this: fault tolerance, because that is the topic we need to justify today. Fault tolerance model of the Spark, because this particular model gives the clarification about how RDD can be seen and how it is going to perform the activities and all. Now, just I am introducing first case, guys. Okay, so this first case is something like this. I am having the RDD1 and R2, and which is nothing but my output. Now, what I'm observing here is when current RDD machine, okay, when current RDD machine is down, when current RDD machine is down, then what should we do? Okay, so now let me clarify what exactly the current RDD and all these things. To explain this scenario, because this is the most generic statement. As I already taken the example, let me jump into that particular example. The thing here is during, okay, whatever the running of the things, during the execution, okay, so just during the execution of current RDD, actually we are saying that we don't know which one is the current RDD. So we need to give the clarity. The clarity here is R2. Okay, maybe sometimes we are running on top of this R1, then the current RDD becomes R1. But whereas if I'm clearly mentioning that my current RDD is R2, that means I'm on it actually. I'm running this R2 presently. So no ambiguity. So out of this particular R1, R2, R2 is the current RDD. So during the execution of the current RDD, that is R2, let's see here. If any one of the partitions, interesting, any one of the partitions, okay, any one of the partitions of the current RDD, of the current RDD, okay, that means R2, current RDD is down. Okay, now this is the scenario, guys. Like, R1 already given the output to this R2. R1 is no more, because as already we have seen, the responsibility of the previous RDD is to allocate the output, now to give the output to the current RDD. Okay, now the thing is, assume that this current RDD is having the partition. In the beginning of the session, we have seen that RDD subdivided into the partitions. Okay, we are having that RDD into the number of partitions. Now the claim is any one of the partitions of the current RDD may be P2 failed. Okay, failed means that partition is not available due to the failure of the corresponding thing, or whichever block, or maybe that is the empty block, or that block may not be accessible, something like that. Okay, that means that RDD is a combination of the partition 1, partition 2, partition 3, but that partition 2 is damaged, which is not available. Okay, so down, then the solution, friends, I'm talking about. Okay, what Spark does is then, okay, RDD partitions, all current RDD partitions like P1, P2, P3 of R2, okay, will be, friends, very interesting, will be deallocated, okay, will be deallocated, okay, so will be deallocated. Deallocated in the sense, meaning of the RAM, because they're all resides on the RAM, friends. We have to remember that. And reinitiated, okay, reinitiated or reinitialized or reloaded, reinitiated or reloaded, whatever the aspects we are having, reinitiated or reloaded in another, okay, so in another slaves, by taking the input from previous RDD. So previous RDD is obviously R1. That means this R1 must be available, okay, because once that output is handed over to the R2, but unfortunately R2 some of the partitions are not available, so that definitely it has to reach to the R1. Okay, so if R1 is not in the RAM, then again it has to start the transformation, friends. Okay, so and in that particular case, the finalization is three partitions: P1, P2, P3. Three partitions are stored in, okay, whatever the partitions we are talking about, stored in three different, okay, whatever the machines, three different machines. Okay, so three different machines. Uh, you may be asking this doubt, excluding the whatever the failure machine, excluding the machine which is down, which is down. Now you can, as a whole, you can observe this point, friends. Like we have started here actually. So there is a situation where R1 output is given to R2, and but unfortunately some of the portion or partition of this particular R2 is not available. Then obviously it is not going to repair that particular partition, because the problem here is without these three integrations, okay, these three partitions should be integrated. Then only I will be able to execute the operations on R2. Okay, whatever the transformations or action we are talking about. So definitely this partition must be available, all the partitions. But the problem here is if some of the partition is unavailable, then all current RDD partitions, P1, P2, P3 of R2 will be deallocated. That is, it is cleared from the RAM and reinitiate the reload in another slaves by taking the input from the previous RDD. Because to execute this particular RDD, definitely it has to, it should be having the previous output, and it is pushed to the next within that partition. Then only we are able to finalize and get the outcome. So these partitions are stored in the three different machines, including the machine which is down, because it is not going to retake this machine, friend, because we have to see that other than this particular machine, it has to allocate these three partitions into different zones. So that is how you can see this particular case one. Okay, quite interesting. So simple, like the scenario we can represent in diagrammatically R1, which is giving output to R2, and this particular R2 is having some kind of the partition P1, P2, P3, but due to some kind of thing, P2 unavailable. Okay, then the solution is okay. So a new slave allocation. Okay, new slave allocation and reinitializing the appropriate partition so that R2 can get the uh, input from this particular R1. It continues the activity. Okay, so this is the basis if any portion of the data is failed in the corresponding RDD. But now the other thing, friends, that such kind of the cases we're having. Now in case two, I'm introducing one more aspect. If previous RDD machine is down, not the current one actually. So if previous RDD machine is down. So pictorially, how I can represent is suppose I'm having R1 and which is leading to R2, which again leads to R3. Maybe my slave, whatever I'm having, multiple slaves we are having. To explain the scenario, so like I'm writing here, guys, during, okay, whatever the execution of R3, okay, during execution of R3, this one, during execution of R3, while taking input from R2, because it should take the input from the R2 machine, that's what we are saying, okay, while just we are taking that R3 is taking the input from R2, just R2, from the R2 RDD, it is taking the input if R2 failed. Okay, if R2 failed, then R2 cannot be here, guys. R2 cannot be reloaded, or it's not the partition entire RDD. Just you have to remember that R2 cannot be reloaded or reinitiated in another machine or in the other machine. Okay, in the other machines, because the problem here is, guys, because if I'm reinitializing this RDD, R1 is also not there in the RAM. You have to remember that. But once R1 handovers the output to the R2, this is no more in the RAM. That is the main important thing. So if R2 fails means where it is going to get the input, there is no RDD actually. It is failed. This R2 itself, because currently we are running R3, and from R2 we are expecting the outcome, and we are taking that outcome as input to the R3, but unfortunately this R2 got failed, disturbed. But R2, to invoke this particular R2, the previous R1 is not there, because R1 has done its work and it submitted the appropriate output to this R2, and it is now the responsibility of the R2 to follow up the activities. So the point is R2 cannot be reloaded in other machines, because what is the problem, friends? Input is R1. Okay, input is R1, where this R1 is not available. Okay, this R1 is not available. Okay, in RAM. We are not having any control over there. Now, the solution, friends, what is the solution opted by the uh, Spark is it has to rerun the task. Okay, so the process should start from the beginning. It should start from the beginning. Or now I am introducing the concept of persisted. Okay, or else the persisted RDD. Okay. Now observe here, guys. What do you mean by persisted RDD? Okay. Suppose I am having certain operations like this, and if I am persisting my RDD, assume that I have persisted this particular R2. Now the point is R2 will be preserved even after completion of the R2 activity. But the common rule is if R2 or R3 are performing some kind of the activity after completion of the activity, definitely it has to remove the, okay, in the RAM by Spark. So that particular practice is there. But whereas sometimes, if I want to maintain a particular RDD in memory, okay, I can do that. Okay, so that will be persisted, though we are after completion of the corresponding aspect also we are allowed to access that particular RDD. Now, okay, whatever I'm talking, just you can see here in case 3, let me put this way. What we are observing in this particular scenario is, suppose I am giving a data flow R1, which is giving output to input to R2, and this R3, assume that, so just I am making use of this R3 in system 3, which is persisted RDD. Okay, persisted RDD. And again, I'm having my R4, R5, and each and every RDD is having a certain slave, okay, allocated so as to store the partitions. Now, this is the scenario, guys. I'm having 5 RDDs, and of course, out of those 5 RDDs, the third is the persisted RDD. Okay, the third is the persisted RDD. Now, the problem here is if a persisted RDD, okay, a persisted RDD machine is down or failed. Now, see the scenario. We are thinking about the persistence where that particular data is available in the random access memory. Now, once you observe this particular scenario, if something happened to that machine itself, okay, so now what is the scenario here, guys? We know that R3 stored and it is persisted, but suddenly S3 is down. Okay, so the problem here is system 3 is down. Then the flow will be re-executed from the beginning. There is no other option, or the available source automatically till R3. So let me write this. If suppose system 3 got failed, then there is important point here, guys. That's what I'm insisting. Then the data flow will be re-executed. Of course, this is nothing new. Definitely, it has to from the beginning. This is quite natural for the Spark, or from the okay, or else from the available source. Available source in the sense, guys, maybe some other RDD would be there. In the beginning of the session, here we have seen some flow of the data, if you observe this. Until this R3 is handing over the output to all the other RDDs, it remains in the RAM. In that particular case, the output is available now. So, in between, if R4 or R6 or R8 got any requirement of the data, then it is going to fetch from the R3. I mean, from the available source means if any such kind of the RDD is available in the memory, then it is going to request that and it is going to get the information. But this is not always the case. If that R3 is also not there, okay, now you see due to some this thing, and there is no available kind of thing from the beginning, it has to execute or from the available source, either of the things available source automatically. Okay, so you need not explicitly mention any kind of thing automatically till R3. So because we are seeing that R3 S3 got failed, okay, till R3 only we are interested to execute. Okay, without performing any action. Okay, without performing action, because first it has to persist that particular R3, okay, and R3 will be most important point, guys, re-persisted, because failure of the S3 should not ruin the persistent behavior of the R3. The problem is for the machine only, not for the R3. So in that particular case, as usual, Spark runs the motto like R1, R2, R3, and before performing any activity, just again it is going to persist. That is the beauty of this Spark specification, guys. In that way, Just it is maintaining, though if any failure is there in the machine where we are running the appropriate RDD in the persistent mode, but still it is able to maintain the consistency. Okay. So again, coming back to case one, only partition failure. All these partitions are distributed to other slaves. Second thing is previous RDD machine is down. Then during the execution of R3, while previous R2 is failed, if it is available, then it is going to use that. Otherwise, if it is not, it cannot be reloading the things because input of R2 is available with R1. R1 output is input of R2. So the process should start from the beginning or at least from the persistent. And we have seen the third kind of thing, the persistence. If any problem is there for the persisted object, then this has to be observed. Okay, any available nearest available source, or else it is going to run the appropriate task from the beginning, and it is going to repersist the appropriate R3 without fail. So before applying any kind of the action. Okay, quite interesting. So definitely, which is really helping us to understand the capability of Spark. Now, but here no ending for the story, guys, because some more cases are there where we need to observe, and this particular thing actually gives us a challenge actually. Suppose I'm writing a data flow here, R1, and I'm having R2, and we are having R3, where there is a machine called S3, which is of course persisted, and then we are having R4, R5. And by default, these particular machines are available in multiple slaves, S1, S2, S3, S4, S5. So while computing R5, so this particular R5, okay. So while we are computing R5, just we are making use of R5, and while taking input from R4, by this time you would have observed hmm, while taking the input from R4, your expectation is correct. If S4 failed, okay, that machine is failed. Then guys, don't worry because most recent update is S4 is failed. Then what you do? Then the input. Okay, so the input is taken from R3 because R3 is not eliminated or cleaned from the RAM because that is a persisted which is available in RAM, and of course reloading because we are dependent on R3, but we are not using the output of R3 in R5. But what we are doing is reloading R4 partitions, okay, whatever the partitions I'm having, okay, in other machine, okay, because this S4 is no more in other machine, and provide input to R5. See, that is the base of the persistent trends. Maybe we can say that I'm having some plenty of the operations, and maybe at any point of time, some of the RDDs or corresponding slave machines might be having their own failure. But due to the persistence, what we can achieve is the persistent RDD is available in the RAM so that we can the appropriate output can be preserved there. So from that, okay, R3 because R4 got failed actually. Here the machine is not available. So definitely uh, R4 must be there because currently we are with R5. So in that particular case, this R5 should pick up the data from R4 only, not from R3. But a strong advantage is we need not restart from R1, R2 and then move to R3, R4 like that, not required. So we can skip that R1, R2 establishment as R3 is already containing the output of those two, whatever the RDDs we're having. And from that particular thing, we can connect with our R4 establishment of the partitions, and which is giving the outcome to the R5. Okay, so this is way how we can manage the aspects. Okay, once we come across with some other case friends, like this is another case which is pretty useful. And now, if you are, I'm giving the data flow like this R1, and I'm having R2, and I'm having R3, R4, R5, and R6. So of course, logically we are notifying the machines as S1, S2, S3, S4, S5. Assume that my S3 is persisted, and as well as my machine S5 is also persisted. Okay, my S3 is persisted and S5 also persisted. So in this particular case, guys, okay, so now again there are two more cases actually. In the first case of fifth case, if R5 machine is down. Okay, if R5 machine is down, then how do you handle this situation? Simple, as from the earlier thing, R3 is persisted, so we can make use of the output of this R3, and this uh, again you need to have this R4 kind of the output. Based on this thing, R5 can be established, and it should be repersisted. It should be repersisted. So the solution for this flow will be re-executed, whatever the flow I'm talking about, from R3 to R5, because R3 is our persisted one. Okay, that is available. So you need not go beyond that R3, because R1, R2 are no more in the RAM, but R3's impact is there. So from that R3 until R5, we have to rerun. Okay, and moreover, the most important thing is R5 will be re-persisted, because this is also one of the important criteria Spark has to take care. It's not only hand over the output to certain kind of the RDDs, but it has to see that any RDD in the failure one is really persisted, and accordingly it is going to perform the activity. Now, just if you refer the same thing, same flow again, R1 with machine 1, because some more cases there. Last case, of course, this is, and R3, some kind of the slave machines, R4, R5, and we're adding R6. This is slave 6. Now, what we are doing here is, guys, the problem here is already we know that this is persisted. Uh, this is also persisted. Okay, this is also persisted. Now, observe here. So I'm introducing one more case in fifth one. This case is something like that. If R3 machine fails, if R3 is machine is down. Now the point we need to observe is if we are at R3 machine, maybe you are in R6 means you are safe. This is persisted. If you are in R4, assume that current machine is R4. Currently you are with R4, but unfortunately this persisted RDD got failed. Okay, in that particular case, if R3 machine is down, yeah, flow will be re-executed. Okay, flow will be re-executed from R1 to R3. Okay, automatically, because earlier to that there are no more persistent objects, so that it has to take from starting of the machine. Okay, just it has to start from this R1, then it moves to R2, then R3, and most importantly that we know R3 automatically, and R3 must be repersisted, and R3 will be repersisted. Okay. So now you can see guys here. So we started with the uh, RDD with partition 1, 2, 3. If any of the partition fails, then again establishment of the corresponding partition in a different slave. This is the first thing we have observed. Second thing is we pretty know that RDD, once it is completed its activity, okay, it is not, suppose you are at RDD 3, these two will be deleted. These two previous RDDs effect is not there in the area. RAM is not containing these things. So in that particular case, if any failure is there, if any problem is there, until that particular thing, we have to re-execute. And again, we have seen some persisted kind of thing. Okay, this particular persisted is something like there is no elimination actually. So suppose if I am having R1, R2, R3, R4 kind of thing, if R3 is persisted, no problem. If any problem is there, then it is still available. Okay. But whereas sometimes this persisted also there is a problem actually. For persisted also, if any problem is there, then again it has to take the decision of the starting, or else any previously available. Okay, any previously available kind of thing. Maybe multiple persistent. Just to have we have seen maybe two persisted kind of the RDDs. Accordingly, it is going to perform the activity. So these are all the criteria, guys, where you can refer in understanding of this RDD, persistence, and fault tolerance. In fact, while studying our Spark architecture also, we have to keep these particular points in mind. And just as a recap kind of thing, so just I'm going back to the specification of this, what exactly RDD. Okay, resilient distributed data set. Now you can easily connect how it is resilient and in what way it is distributed. And basically, Spark data objects, we can name that as RDD orientation. And RDDs, again, the main aspect related to this is RDD is subdivided into the partitions. And these are all partitions distributed across the multiple RAM because it is in-memory computing of multiple slave nodes and are processed in parallel. So at the moment, if I'm talking about the programmatical aspect, because ultimately, as a developers or a data engineer or data scientist, we need to establish some programmatical constructs. So that RDD programming style is a data flow. So let us try to understand the data flow. Data flow is a sequence or collection of the pipes. A pipe is something like that, which is a data operation. Maybe you can perform loading of the data, transforming of the data, filtering the data, grouping the data, merging the data, etc. Like that, we can perform multiple activities. So, in a pictorial representation, RDD is having set of the partitions which are running on some kind of the slaves in memory, and these particular things maintain the data flow in terms of the pipes. And these pipes may be connected or established with loading, filter, group by whichever the operation. Now the data flow is executed in sequence because this output generated by the earlier RDD should be connected to the next coming RDD. Then only it is following up the activity. Parallelism only possible. Suppose if you are having multiple partitions around 20 or some more than those kind of things, they can run parallel, provided there should be no dependency of one RDD output with another RDD's input. Okay, so in that particular case, we need to run or Spark need to execute that particular code in the sequential aspect. So in Spark, the data flow is executed in sequence, that is RDD by RDD, one after another with in-memory computing. We pretty know that. And feature and persistent features. Okay, in-memory computing and persistent. Persistent, we are going to talk. Persistent means just if you are referencing the any RDD orientation, if I a general example for this is After running of that RDD, after handed over the output of that RDD to the new RDD, the previous one is not been available in the RAM. Okay, so if that is not the case, and if you want to keep that particular RDD even after completion of that activity, then you can persist that. Okay, RDD that persist with that. You can maintain that RDD even after completion of the task also. And basically, guys, entire Spark is revolving around two important things. That is the transformations and as well as the actions. On top of this RDD, two types of operations were performing. That is the transformation and as well as the action. So if I'm talking about these transformations again in Spark orientation, maybe each element like map and flat map, where I want to apply some kind of the conditions or where I want to apply some sort of operations on each and every element of the storage, then I can go ahead with the map or flat map kind of thing. Whereas sometimes, the filter or applicability of the conditions, in that case, the filter based transformations and then aggregation, like some sort of finding out of the summation, max, min, or group by, all these kind of things can be observed with respect to aggregation. Okay, it all depends on the requirement, guys. Okay. And actions, when the action is performed on RDD, then only the data flow will be executed. That we pretty know, the triggering of the activity. Examples, collect, count, save as text file, all these things. This is important, guys. Like multiple RDDs are there, and there is a multiple flow of the activity. But still, so just as a kind of the dependency, you can observe what exactly this flow is going to work out. And after handing over the appropriate output to the next coming RDD, the previous one is no more in the RAM. With that point, we observed some five different techniques, how these kind of the fault tolerance model can be observed related to our RDD orientation. Okay, that's all, guys. Some other with some other topic, I'll come to you. Okay, thank you.
Thank you, Dr. Pawan.
Bye. Thank you.
Bye.
Bye. Okay, bye.